Hello and welcome to this presentation related to remainder theorem. In a previous presentation we considered polynomial division, where we divided a polynomial expression here by a linear expression shown here and determined the answer to the problem, which involved calculating the remainder. In this presentation we're going to derive remainder theorem, which will find in a more simplified way the remainder of such a polynomial division, shown on the right hand side of the slide. There is some underpinning knowledge it's preferable to be aware of before reviewing this presentation. Firstly, to understand quadratic and cubic equations, their structure and form. Secondly, how to determine roots and factors of quadratic and cubic equations. Thirdly, it's preferable if you understand the process of polynomial division, as this underpins the derivations we're going to review in this presentation, although it's not essential to understand polynomial division to apply remainder theorem. And it's also useful if you reviewed factor theorem, a similar technique that used specifically to find factors of quadratic and in particular cubic equations. For reference, there are separate presentations available for all of these topics. Here's the presentation overview. We initially commence by stating some definitions and terminology that will be used throughout the presentation, and also very briefly recap some underpinning knowledge and techniques. Then we compare and contrast factor theorem from our previous presentation with remainder theorem, the essence of this presentation. I have included a proof associated with remainder theorem for quadratics. I know most students will not be particularly interested in the proof, but I've tried to elaborate on standard textbook proofs to illustrate how remainder theorem is derived. We then have a section where remainder theorem is actually applied to solving quadratic problems, and then very briefly show remainder theorem proof considering cubics, and then we have a section where we apply remainder theorem to solving cubic problems. The presentation ends with some tutorial questions for you to attempt at your own pace, and for reference here are the approximate start times related to the various sections contained within the presentation, should you want to skip to a particular section. The presentation does contain much background material and underpinning theory related to remainder theorem, so some students may initially prefer to skip directly to the tutorial questions section, where the basic procedure of applying remainder theorem in a few simple steps is outlined. But if they need further background knowledge, they can then refer to these other sections as required. I'm just very briefly going to outline some definitions and terminology that will be used throughout the presentation for your reference. Firstly, the term polynomial. This relates to an algebraic expression having two or more terms. So for example, polynomial expression shown here is x cubed plus 3x squared minus 5x plus 1. There's four terms in this polynomial expression, has variable x, and as it's cubic, the highest power of x is 3. In the illustration at the bottom of the slide, again we have a polynomial shown here of ax squared plus bx plus c. This is a quadratic expression having three terms and the highest power of the variable x is 2. Linear expression. This is an algebraic expression with the highest exponent of the variable being unity. So for example, in the expression ax plus b, where x is the variable, the power of x is 1. We don't write the ones, but they're there. In the expression x minus 2, again the highest power of x is 1. And in the expression 5t plus 3, the highest power of variable t is again 1. So those are all linear expressions. If we again consider the bottom of the slide, we have a linear expression shown here of x minus p. And of course again the x is to the power of 1. Term dividend. This relates to the number being divided. So in the calculation 12 divided by 4 is equal to 3, then 12 is termed the dividend. At the bottom of the slide here we can see that the ax squared plus bx plus c polynomial is the dividend, the top line or the numerator of our calculation. The divisor, this is the number by which another is divided. So in the calculation 12 divided by 4 is equal to 3, then 4 is termed the divisor. At the bottom of the slide, the linear expression x minus p is the divisor, the bottom line or the denominator of the calculation. Term remainder, this is the quantity left over after a division operation. So if we consider the calculation 11 divided by 4, 4 divides into 11 twice completely, give us 8. with remainder 3. Definitions continued. Again, this is essentially recap. Term factor, that's a whole number that exactly divides into another whole number. So 3 is a factor of 12 because 3 divides into 12 4 times. And also we could say that 4 is a factor of 12 because it divides into 12 3 times. Root. The root of an equation is also known as the solution to that equation. So for example, x equals to 1 is the root of the quadratic equation shown below, the x squared minus 5x plus 4 equals 0. If we state the value of 1 for x in the equation shown here, we see it evaluates to 0. Note, to find a root, we simply equate the factor to 0 and solve the equation. So equating the factor to 0 is our factor x minus p, it now equals to 0. And then rearranging, we solve for the root x, so in this case x is equal to p. Again, a recap here of factors and roots. We have a quadratic equation shown in the graph below. It's been factorised here into x minus 2 multiplied by x plus 4. Those are the factors. Note for reference that the negative 2 and positive 4 shown here in the brackets are both factors of the constant negative 8. From the previous slide, having a factor of x minus 2, equating x minus 2 to 0, we see that the root is positive 2. The positive 2 root is shown here. It's where the quadratic curve crosses the x-axis. And again, if we have a factor of positive 4, we can show that equates to a root of negative 4. So again, here's our root, negative 4. So in general terms, a factor of x minus a equates to a root of x equals to a. And the same for a cubic graph shown here, or the cubic equation, y is equal to x cubed minus 7x minus 6. We have three factors, x minus 3, x plus 1, x plus 2. So we can see that the factor x minus 3 would equate to a root of positive 3, shown here. The factor x plus 1 equates to a root of negative 1, shown here. And the x plus 2 factor equates to a root of negative 2, here. Again, note that the negative 3, the positive 1, and the positive 2 are all factors of the negative 6. Negative 3 multiplied by positive 1 multiplied by positive 2 is negative 6. Here's an overview of factor theorem and remainder theorem. Factor theorem and remainder theorem are both related to polynomial division, but they serve different purposes. Remainder theorem determines the remainder when dividing a polynomial, function of x, by a linear expression, x minus a. We will show that the remainder in this case is a function of a. Factor theorem determines whether the linear expression x minus a is a factor of the polynomial, function of x, by checking if the function of x equals to 0. Just note for reference that remainder theorem can also determine if a linear expression is a factor of a polynomial when the remainder is 0. Purely for reference, here's an extract from our previous presentation related to factor theorem. This was example 2 from that presentation. We're trying to factorise the cubic expression x cubed minus 7x minus 6 and use this to solve the equation when the expression equals to 0 here. And this is essentially a trial and error approach to find the root and then the associated factor. So here's our trials on the left hand side here, x equal to 1. So wherever we have an x, in our expression we'll replace that with 1. The x cubed term minus 7x minus 6 equals to negative 12. So that doesn't equal to 0, so no root found. So let's try another value of x. We try x equal to 2, wherever we have an x in the expression, again that doesn't equal to 0. So try x equal to 3. When inserting 3 for x in the expression, we find that does evaluate to 0. So as the answer is equal to 0, then x minus 3 is a factor. So factor theorem specifically tries to find factors of our given expression. Again, notice that all of these numbers are factors of the -6. So that's how we begin to consider the numbers we could use in factor theorem. So let's consider remainder theorem for a quadratic equation. So given a general quadratic expression, the form ax squared plus bx plus c, which we're going to divide by the linear expression x minus p here, where p is any whole number, then by the process of long division, i.e. polynomial division shown here, here's the ax squared plus bx plus c expression, that's actually our dividend. Here's our x minus p linear expression, that's our divisor. We can show that remainder is of this format here. So this is the remainder, but notice there's a sign change of p. P in the original linear expression is a negative value, but p in the remainder format shown here is a positive value. If we expand the bracket shown above, we form the expression ap squared plus bp plus c, and that's termed remainder theorem. So when remainder theorem is applied to a quadratic equation, quadratic expression, we find that if ax squared plus bx plus c is divided by x minus p, the remainder is of the form ap squared plus bp plus c. So essentially, we find the remainder by substituting the value of p for x in the dividend. So essentially substituting the value of p for x in the dividend, that's the numerator, calculates the remainder. That's been derived from our polynomial division, shown here. So an overview, our dividend is in the form of a quadratic expression, ax squared plus bx plus c, and our remainder is also of the form of a quadratic expression, being ap squared plus bp plus c. So in essence, the dividend can be considered a function of x, and the remainder is a function of p. And note the remainder is found by substituting p for x in the dividend, and to find the value of p, we equate the divisor to 0, this is the divisor, and we solve. So x minus p is equal to 0, so the solution is x is equal to p. And so p has effectively changed its sign between the divisor, x minus p, to the value of p used in the remainder theorem, which would be positive p. Remainder theorem for quadratic equations continued. Example 1q shows us the polynomial division related to the 2x squared minus 3x plus 6, our dividend, divided by the linear expression x plus 2, our divisor. If you've not studied polynomial division before, then you will not be able to follow the process here. But just note that the remainder calculates to be 20, shown here. So example 1q continued here. So if we plot the equation y is equal to 2x squared minus 3x plus 6, here's our quadratic curve. We know the remainder is 20, this point here, and that equates to an x value of -2, shown here. So the p used in remainder theorem is -2. And again, if it helps you in your application of remainder theorem, we can think of this as being a change between the positive p that's in the divisor here and the negative p that's used within remainder theorem. Remainder theorem for quadratic equations continued. Let's now check the remainder that was found using polynomial division on the previous slide by using remainder theorem. So repeating the calculation, we're asked to divide 2x squared minus 3x plus 6 by x plus 2. You can clearly see this is of the form ax squared plus bx plus c divided by x minus p. We know from remainder theorem the remainder is given in the form of ap squared plus bp plus c, where a in this case is 2, b is -3, and c is +6. And note that p to be used in remainder theorem is actually -2. So inserting p into the dividend of the expression, we simply put p wherever there was an x, so -2 here in the 2x squared term, and -2 here in the minus 3x term. That evaluates to a remainder of 20. And that's what we found on the previous slide. So the remainder using remainder theorem is the same as that found using polynomial division. Our 20 here compares to our 20 here from polynomial division. However, note that should the remainder prove to be 0, then the divisor x minus p is a factor which is useful when factorising expressions such as quadratics and particularly cubics. Let's consider example 2q. It says on solving 4x squared plus x minus 5 divided by x minus 1, we've got to show the remainder is 0. So here's our solution. The 4x squared plus 1x minus 5 is our dividend, it's a quadratic expression, and the x minus 1 is our divisor, that's our linear expression. And from remainder theorem, we know the remainder is of the form ap squared plus bp plus c. In other words, to find the remainder, we insert the value of p or x in the above dividend. To find the value of p to use, we equate the divisor to 0, solve for x, and that's the value of p that we will now use in remainder theorem. So essentially inserting p into the dividend, we find the remainder is 0. Now if the remainder is 0, then x minus 1 is a factor of this quadratic, so the x equals to 1 is a root. So as exercise 1, using remainder theorem, we've got to find the remainder of 2x squared minus 3x plus 4 divided by x minus 2. Given the answer is 6 for the remainder, and for those of you who understand polynomial division, you can check your answer using polynomial division. I would encourage you to start the presentation, attempt exercise 1. There's a hint, here's the remainder theorem, so this is our dividend, here's our divisor, and here's the remainder. The full work solution is shown on the following slide. Here's exercise 1, the solution. So here's our dividend, 2x squared minus 3x plus 4, our divisor, x minus 2. So for remainder theorem, we need to insert the value of p or x in the dividend. In this case, the value of p will be positive 2. So inserting 2 into the above dividend, we evaluate the remainder, which is 6. Note that we can check this answer using polynomial division. So for reference, exercise 1 solution using polynomial division, again we can show that the remainder is 6. Let's now consider remainder theorem, but this time applied to cubic equations. So remainder theorem applied to the cubic equation states the following. If we have a cubic expression, ax cubed plus bx squared plus cx plus d, and we divide it by a linear factor, x minus p, the remainder can be shown to be of the format ap cubed plus bp squared plus cp plus d. Again, notice there's a change of sign between the negative p in the divisor and the positive p shown in the remainder. So essentially, as for quadratics, the remainder is found by substituting the value of p or x in the dividend. So we note that the dividend is a function of x and the remainder is a function of p. And again, to find the value of p, we equate the divisor to 0 and solve. So x minus p is equal to 0, solving x is equal to p. Once again, we can see the change of sign. P in the divisor, essentially a negative p, and the p that we use in the remainder theorem is a positive p. For reference, I've shown the proof of remainder theorem for a cubic expression here using polynomial division. So here we're dividing the cubic expression by a linear expression, and we show that the remainder is of the form ap cubed plus bp squared plus cp plus d. I'll let you review this at your own pace. Here's example 1c. We've got to find the remainder of 3x cubed plus 2x squared minus x plus 4, that's a cubic expression, divided by x minus 1. So in this case, our dividend is the cubic expression, our divisor is the x minus 1. So using remainder theorem, we have to insert p or x in the dividend. So to find p, we let the divisor x minus 1 equal to 0, solve for x. In this case, p is equal to 1. So inserting the value of 1 into the dividend above and evaluating, the remainder is 8. And we can again check this using polynomial division. Here's example 1c, again trying to find the remainder of our given expression, but this time we're using polynomial division. Here's the actual polynomial division calculations undertaken, and we can clearly see the remainder is 8, as found from Remainder Theorem, shown here. Here's a plot of the curve y is equal to 3x cubed plus 2x squared minus x plus 4. That's the dividend given. We were dividing by x equal to 1 here. We found the remainder was 8. And from the graph we have a remainder of 8, which occurs at a value of x equals to positive 1. Example 2c, we've got to find the remainder of 2x cubed minus 14x minus 12 divided by x minus 3. So our dividend here is a cubic expression, divisor is x minus 3. So we're going to apply remainder theorem, insert the value of p for x in the dividend, noting that p is equal to positive 3. So inserting p in the above dividend, the remainder evaluates to be 0. So hence, as the remainder is 0, then x minus 3 is a factor. The one root of this cubic equation is x equal to 3. Again, the remainder can be checked using polynomial division. So for reference, here's polynomial division applied to example 2c. Again, notice the format of the dividend. I've included the 0x squared term divided by x minus 3. So for those of you that understand the polynomial division technique, see I need the 0x squared term in the calculations dividing by the x minus 3. But the remainder again can be shown to be 0. Example 2c is a plot of the equation y is equal to 2x cubed minus 14x minus 12 as our dividend. And the curve shows we have a 0 value when x is equal to positive 3. Here's exercise 2. Using remainder theorem, find the remainder of 3x cubed minus 2x squared plus x minus 5 divided by x plus 2. We're given the remainder is negative 39. For your reference, here's remainder theorem applied to cubic equation. I would encourage you to stop the presentation and attempt exercise 2, but the full work solution is shown on the following slide. Here's exercise 2, solution. From this problem we have a dividend, that's an expression in a cubic format, a divisor, x plus 2, from x minus p, and from remainder theorem we now insert p for x in the dividend. So in this case p is equal to negative 2. So to find the remainder we simply insert the value of p for x in the dividend given in the problem and evaluate the remainder is negative 39. And purely for reference, here's exercise 2, solved with polynomial division, and again we can show the remainder is negative 39. Exercise 3, we're asked to show that the following have no remainders, so we're asked to determine all the factors and the roots. We're given two problems to solve in exercise 3. Problem 1, we have x cubed minus 2x squared minus 5x plus 6 divided by x minus 1, and the same dividend here, but this time divided by x plus 2. Answers shown in the square bracket here for the factors and for the roots. Again, for ease of reference, here's remainder theorem applied to a cubic equation. Given our dividend in this format, divisor, the remainder is given in this format. I'd encourage you to stop the presentation and attempt exercise 3, but the full work solution is shown on the following slide. Exercise 3, part 1, solution. So for part 1, we're given the dividend, a cubic expression, divided by x minus 1, divisor. So from remainder theorem, we'll insert p for x, and our dividend, note that p is equal to positive 1 in this case. So inserting positive 1 for x in the dividend, we find the remainder is 0. So as no remainder, our divisor x minus 1 is a factor, and equating the factor to 0, we find that x equals to positive 1 is a root. Here's exercise 3 part 1, shown solved using polynomial division. I'll let you review the polynomial division process at your own pace, but again the remainder is shown to be 0. Exercise 3, Part 2, Solution. Part 2, we're given a cubic expression for a dividend, linear expression for our divisor. On remainder theorem, insert p for x in the dividend. Note that p is equal to -2. So inserting -2 for x in the dividend, the remainder is 0. So again, there's no remainder. X plus 2 is a factor, and equating the factor to 0, we have a root is x equals to -2. Exercise 3, solution continued. For reference, to find the third factor of our cubic expression, given above in the question, having already found the first two factors of x minus 1 and x plus 2 from our previous slides, we can find the third factor by considering the following. We know we need an x cubed term at the beginning of the expression and a positive 6 constant at the end here. So considering the factor x minus 1 and x plus 2, if we multiply x by x, we have x squared, so multiply by another x and we will find x cubed. So the first term in our third factor must be x, and to get positive 6, having already established we have -1 and positive 2, that multiplies to give -2, then the final term in our third factor must be -3. So now we have the third and final factor for our cubic. So again, think of the expansion of the brackets. X multiplied by x multiplied by x will be x cubed, and -1 multiplied by positive 2 multiplied by -3 will be 6. Exercise 3, solution continued. In part 3, as I've labelled it here, we can now check the solution on the previous slide for the third factor. We're given our dividend, and now we use the divisor of x minus 3 determined on the previous slide. Applying remainder theorem, inserting p for x in the dividend, noting that p is equal to positive 3 here, inserting p in the dividend. We calculate the remainder is 0. So as no remainder, x minus 3 is a factor, breaking the factor to 0. X equals to 3 is the root. Here are now some tutorial questions related to remainder theorem for you to attempt. I'll show you the solution to some of the questions, but the remainder, no pun intended there, I will leave for you to solve at your own pace. So question 1, got to find the remainder using remainder theorem of a polynomial in the form of a quadratic divided by our linear factor x minus 2 here, and part b, the same quadratic expression, but this time divided by x plus 1. The answers and the remainders are shown in the brackets on the right hand side. For ease of reference, use remainder theorem applied to a quadratic. I would encourage you to stop the presentation and attempt question 1, but I'll briefly show you the full solution on the following slides. So here's question 1, solution. So for part A, we're given 3x squared minus 4x plus 2, that's our dividend. The divisor is x minus 2, and from remainder theorem, we now insert the value of p for x in the dividend. As the divisor is x minus 2, then the value of p will be positive 2. So simply now inserting 2 into the above dividend, becomes 3 times 2 squared minus 4 times 2. Evaluating, the remainder is 6. I'll let you review all following solutions at your own pace. And question 1, solution to part B, shown here. The remainder is 9. Notice again here the change of sign between divisor and p. Here's question 2. We have to find the remainder using remainder theorem of part A, cubic expression divided by the linear expression of x plus 2, and part B, the same cubic expression divided by the linear expression x minus 3. Remainders are shown on the right hand side, a reference, and here's the remainder theorem related to a cubic to calculate the remainder in this form. Again, I would encourage you to stop the presentation and attempt questions, but the full work solutions are shown on the following slide. Question 2, solution to part A. Remainder is negative 39. And solution for part B, remainder is negative 29. Again, I'll let you review these solutions at your own pace. Question 3, using remainder theorem to this time find the factors of the cubic expression x cubed minus 6x squared plus 11x minus 6. The three factors are shown here in the brackets. To find a factor, the remainder must be 0. I'd encourage you to stop the presentation and attempt question 3, but the full work solutions are shown on the following slides. So question 3 is the commencement of the solution. In a way, we're applying remainder theorem here as a like factor theorem. Given our cubic expression shown here, we need to determine the values of x that will leave the remainder, in this case, equal to 0. So it's essentially a trial and error process. We need first to consider factors of the constant. That's d is negative 6 in this case. We know that the coefficient a is 1. We don't write the 1s as such, but of course there is a 1 in front of the x here. With a is equal to 1, possible factors of the negative 6 are 1, 2, 3, 6, and negative 1, negative 2, negative 3, and negative 6. So when we're multiplying our three constants together, the value must equal to negative 6. So I will try values of negative 1, negative 2, and negative 3, because that evaluates to negative 6. Question 3, solution continued. Here's part 1. So let's try a divisor of x minus 1. So here's our cubic dividend divided by x minus 1. Applying remainder theorem, inserting p or x in the dividend, noting that p is equal to positive 1. Positive 1 replaces the x in the dividend above. We find the remainder is 0. So no remainder, find x minus 1 is a factor, and x equals to 1 is a root. Question 3, solution continued. Here's part 2. This time we're trying a divisor of x minus 2. So dividing our dividend by x minus 2. I'll let you review the solution at your own pace. Solution process the same as on the previous slide for part 1. Again, there's no remainder, so x minus 2 is a factor, and x equals to 2 is a root. And question 3, solution continued for part 3, this time trying a divisor of x minus 3. I'll let you review the solution at your own pace, but again we find the remainder is 0, so we have a factor and a root. Hence now we've factorised the cubic expression given into 3 factors. Question 3, solution continued. But again, there is an element of educated guess within the process to try and determine the various factors. I'll leave you with question 4 to attempt at your own pace. Given a cubic, you have to find the factors of the cubic, as shown here, and determine the roots. I'll let you solve question 4 at your own pace. No solution is provided here. I will provide you with a brief hint if it helps you progress the question. Question 5, basically solve this expression using remainder theorem, answer shown in the bracket here. And question 6, posing a slightly different problem here, we're asked to determine the value of the coefficient labelled as b if x plus 2 is a factor of the polynomial expression x cubed minus bx squared plus 7x plus 10. There's a hint in the question, as x plus 2 is a factor, then the remainder is 0. So knowing this, we are able to generate a simple equation and solve the equation for coefficient b. Answer for b is shown in the bracket here. Here's the bibliography used to help generate this presentation. Some very good reference sources. So that concludes the presentation related to remainder theorem, which I hope has been of use to you, and thank you for viewing.